Elroy Galbraith, and the title of the talk is The Ocean Environment-Bacterioplankton Nexus. Dr. Galbraith, you have the stage.
Yes, hello everyone. Thank you for joining in. So I will just begin by sharing my screen. I recorded my presentation. So share sound. Okay. I believe you should be seeing now.
Yes, we can see it.
Okay, so let's. Greetings, my name is Elroy Galbraith and I'll be presenting on the Ocean Environment-Bacterioplankton Nexus, a study I conducted in collaboration with Professor Matteo Convertino. Coral reefs and other marine and terrestrial ecosystems are facing existential threats from anthropogenic stressors like climate change, nutrient pollution, overfishing, etc. So there is a growing need to be able to signal and predict ecosystem-wide tipping points. Now, global research indicates that the structural and functional dynamics of the microbiome, a community of microscopic biotic organisms living within the marine systems, they drive biogeochemical cycling and they are predictive of environmental perturbation. However, no one has as yet devised a way of measuring ecosystem health given the complex relationship between the microbiome and the environment. So we attempted to derive a marine ecosystem health signature considering the optimality in community structures of free-living aquatic bacterioplankton and oceanic physico-chemical drivers. But why a complex system is manifested by scale freeness in their distributions? The microbiome or bacterioplankton system is a complex system whose PDFs are biological processes producing information that spreads via a network. The envirome is a collection of physical, chemical, environmental drivers, which is also a complex system whose PDFs result from nonlinear interactions among these physico-chemical drivers. The ecosystem state or ecosystem health is a function of the state of its microbiome and its envirome. So by evaluating the amount of scale freeness in both these functional networks, we should be able to derive signals of ecosystem health. Of interest as well would be being able to identify the specific bacterioplankton species or physico-chemical factor that is responsible for the ecosystem state, as well as understanding how the bacterioplankton community specifically is responding to environmental pressures within this framework. Here I provide an overview of our methodology, which moves from biotic and abiotic data through inferred network structures into a phase space that evaluates the ecosystem health. Our model begins with the ecosystem data. In this case study, we used bacterioplankton and environmental data from 7 sites within the Great Barrier Reef. Next, using transfer entropy, we inferred weighted directional networks of the bacteriome and enviromes for each location. Each node in this network would represent either a species or environmental variable, and they would be connected by a link if the transfer entropy between their time series was greater than 0. The transfer entropy here would be the total nonlinear, asymmetrical, and asynchronous interaction between pairs of species or environmental drivers. It represents a quantification of the extent to which species X or environmental variable X causes species or environmental variable Y. Then we analyze the structure of these networks to plot a phase space, which indicates the health of an ecosystem by signaling its departure from optimality, considering the structure of its bacteriome and envirome. A little bit more on how the phase space was constructed. First, we plotted the exceedance probability distribution of the transfer entropies for the bacteriome and the envirome. We observed that these distributions were log linear, so we fitted an exponential distribution function. Lambda, the scale parameter, was used as the optimality indicator. An ecosystem plotted in the lower left-hand corner would be considered more optimal. Lower lambda corresponds to more structured interaction networks with higher scale freeness. So notice how Fi, closest to optimality, presents a more structured network, while TT3, furthest from optimality, has a less structured network. Complexity theory tells us that systems that look more like Fi and less like TT3 are in a critical state where they operate optimally and are more resilient to perturbation. Besides facilitating ecosystem-wide diagnosis, our focus on network dynamics reveals community patterns that are also informative for evaluating the biological system. We discovered a Kleiber's law-like scaling relationship between the abundance of a species and its outgoing transfer entropy. The amount of information a species distributes into the network is proportional to its abundance, raised by a factor of about 0.2 on average. Now, the outgoing transfer entropy can be used as a proxy for metabolic functioning within the biologic network, as it reflects the impact of a species on all others. So here what we're showing is how the structure of the community affects the functioning of the node. But even this effect is balanced within the community. Interestingly, this scaling relationship appeared to vary by geomorphology and environmental pressure. Biodiversity, another metric of community health, is known to be largest in deep habitats like the marine lagoon, here in purple, compared to shallow habitats like the riverine sites, like TT1, TT2, and TT3, the light blue, dark blue, and pink points here. Notice here that the exponent is highest the furthest from shore. Biodiversity also varies with exposure to environmental pressure, and what we observed was that the closer a site is to the river, which is highly impacted by agricultural runoff, the lower the exponent. So we don't know what the ideal exponent is, but these patterns appear to be consistent with other evaluations of ecosystem health and are worth further study. So there is a relationship between the structure of the biotic network and the function of the species in the community that appears to respond to geomorphology and environmental perturbation. Of course, our method allows for identifying the specific nodes and interactions that are likely responsible for ecosystem state. Keystone nodes, whether species or environmental factors, are those with the largest amount of interaction, both incoming and outgoing, as well as the largest number of connections. So these will be the species or environmental factors which are interacting the most and are thus most responsible for the network structure. And in keeping with the theme of information flow during interactions, we identified what we are calling keystone links. Now, these are based on the link salience of a pair of nodes in the network. A salient link is one that is part of the shortest path between any other pair of nodes. So if a salient link is removed, the path between two nodes is lengthened, and the functioning of that network then is substantially changed. So what we observed as well was that the most salient links in a network tend to involve relatively rare species connecting a central species based on our weighted network centrality metric and a more peripheral species. So in conclusion, there are structural signals within the bacteriome and envirome for ecosystem health diagnosis. The state of these communities are regulated by weak ties involving strongly interacting nodes, but there is a biogeographic pattern to these community interactions that may be resulting from geomorphology and environmental pressures. Our major contributions include a metric for ecosystem diagnosis that is based on optimality divergence in ecosystem microbiotic and abiotic communities. A novel Kleiber's law-like pattern derived from information theoretic measures, and a novel means of identifying responsible nodes given distribution of links and fluxes. With more data from a variety of ecosystems and locations, we could begin to populate this phase space to gain a clearer understanding of when an ecosystem is approaching or departing optimality. Within this framework, we can advance our understanding of the structure and function of microbes, examine how they interact with their environment, and how we can decode these complex systems for holistic ecosystem diagnosis.
Thank you very much for
Thank
your
you.
talk. If there are any questions? Are there any questions? Yes, please.
So, as I understood, you are postulating lambda as a possible indicator for ecosystem health, but as yet it's unproven if it's correlated with ecosystem health. And the question is how you would define ecosystem health, or did you want to define ecosystem health through values of lambda, which are very kind of removed from the actual ecosystem structure? These are some just slopes of the distribution of the interactions, or
So that's correct. It's more decoupling from looking at the ecosystem straightforward, but looking more at the distribution of the networks themselves. Understanding that if the network is structured in a certain way, structured in an optimal way, then it should manifest as a particular kind of distribution with certain slope, a certain slope parameter or scaling parameter. In our case, because the metric that we were looking at, transfer entropy, presented as exponential, that's why we use lambda. If it turned out, for example, that it was very scale-free, very power law in its distribution, we would have called it something else, but essentially what we're looking for is that slope. How much scale freeness is present in the distributions. If it's very scale free, then you're looking at a system that is critical and is so operating, especially in biology, at a very critical state. If it's far from scale freeness, then it's supposed to be operating poorly. And when you look at the networks themselves, that's what was being presented. So that's why we think it's an ideal way. This way, we don't have to think about the biology. We don't have to think about the genetics. We just have to think about how the network is functioning and structured.
Okay, thank you very much. we have to go to the next talk, and the next talk will be delivered by Juan Roja, and the topic is Earth system interactions amplify human impacts on planetary boundaries.
Thanks everyone. My colleague Steve couldn't make it to the conference, but he has recorded a video. We'll play it out, and at the end, I'm happy to try to answer questions or give him his email for further inquiry.
A researcher at the Stockholm Resilience Center at Stockholm University in Sweden, and I'd like to tell you about this paper that I published with several co-authors earlier this year. The planetary boundary framework is a popular way for representing the big global sustainability issues that we're facing worldwide today. It maps out it maps out 9 of these big global sustainability issues. So you can see, for example, climate change, biosphere integrity, which is basically biodiversity loss, freshwater use, land system change, so on and so forth. It then identifies safe limits for the extent to which humans can interfere in these Earth systems. This is the blue circle. And then also assesses at the globally aggregated scale the extent to which humans are currently perturbing those Earth systems. So you can see that for several, we are well beyond the so-called safe operating space. I'm not going to go through these line by line, but these are the specific variables and numbers behind the planetary boundaries.
We cannot hear you.
I'm sorry, it seems to be a problem with the video. It's running on my computer, but it doesn't.
I cannot, also the video has frozen.
Yeah.
Does Roja? Dimitra, what's happening?
So the planetary boundary framework has
try to share again and show the video.
Policy, education, and academia. But one
now, do you hear it?
Yes, yes.
Thing it doesn't do is it doesn't take account of the interactions that we know to exist between all these different components of the Earth system. So for example, climate change will affect just about everything else. Loss of land area, forest area will affect climate change and probably biosphere integrity as well. So the purpose of this work was to try to put the knowledge that we have about Earth system interactions into the planetary boundary framework. So we started off with a survey of the interactions between the planetary boundaries. We then took that survey and built a simple feedback model to look at the consequences of interactions between the planetary boundaries, in particular, their effects on the safe operating space for humans in the Earth system. This is the list of co-authors. And just to set the scope, we considered almost all the planetary boundaries. 2 changes that we made were that, first of all, instead of having just one variable for biosphere integrity, we split that up into land, freshwater, and ocean biosphere integrity, since those components of the biosphere operate quite distinctly. And also we ignored the novel entities planetary boundary, which is an important one, but very hard to quantify. And this is the basic picture you should have in your mind when thinking about the interaction. So in the conventional planetary boundary framework, we have direct pressures on the Earth system, which lead to the total human impacts and then result in changes in the control variables that are represented in the planetary boundaries. What this work aimed to do was, first of all, recognize that there are biophysical interactions between the planetary boundaries, where a change in a control variable will then go and affect the size of another control variable. And I mentioned some examples of them before. But taking a social ecological perspective on the Earth system, we also sought to account for reactive human mediated interactions, where a change in the biophysical state of the Earth system causes a change in human behavior that causes a change in a different component of the Earth system. And also sequential human-mediated interactions, which is basically where we have a driver that affects more than one component of the Earth system at the same time. And just a brief note that all the results I'll be talking to you about now are in normalized units, where a value of 0 corresponds to pre-industrial values and 1 corresponds to values at the planetary boundary. So our first step was to do a survey of interactions. We surveyed the literature systematically. We also supplemented that with our own knowledge of the literature. Just some caveats are that many of the interactions you can imagine are important, but are still highly unconstrained in terms of how strong specifically they are. And we've also only looked at interactions involving the planetary boundaries. There are many other components of the Earth system that have important interactions that we haven't accounted for. So I'm just going through some of the interactions that we found. So first of all, and maybe most obviously, we have impacts of warming from climate change on land, freshwater and ocean biosphere integrity. We have impacts of anthropogenic atmospheric carbon dioxide on ocean acidification and thereby ocean biosphere integrity. We've got climate change, land system change and aerosol loading all changing rainfall runoff patterns and thereby affecting freshwater availability and biogeochemical flows. We have eutrophication in freshwater and ocean systems due to nutrient inputs and freshwater extraction. We have climate change due to carbon emissions, changes, loss of biodiversity, changes in the marine biological carbon pump from acidification and from warming, and also due to changes in freshwater as well. We also identified some sequential human-mediated interactions, that is parallel drivers, that mostly involved the food, energy, water nexus, and some reactive interactions as well. So this is our map of the interactions that we had identified within the Earth system. First thing that we might notice is that the planetary boundaries are densely interconnected. So we found quantitative evidence for 39 out of the 72 possible interactions. So there's quite a lot. We were able to, beg your pardon, we found evidence for 39 and we were able to quantify 29 of those. Most of those are amplifying, where pressure on one component of the Earth system leads to increasing pressure on another component of the Earth system. The only ones that weren't were the ones that I've outlined in black in the slide there. And our results also support identifying biosphere integrity and climate change as the two core boundaries, the two core parts of the Earth system that all other parts interact with. And there's evidence for that by seeing how much of the circumference of this circle is taken up by the biosphere integrity variables and climate change. That's another way of representing how biosphere and climate are at the core. So we then constructed a simple feedback model to assess the consequences of interactions. This feedback model assumes equilibrium and no dynamics. Those assumptions could be relaxed, but would require more data. So the first thing we did was to assess how much interactions have amplified impacts on the planetary boundaries. And you can see that biophysically mediated interactions have had a very large effect, sequential and reactive less so. But the main result that I want to bring your attention to is this one. Here we have aggregated planetary boundaries together into two groups, those related to agricultural pressures on the bottom axis and those related to climate change on the vertical axis. Without accounting for interactions, the safe operating space, that is the region where no planetary boundaries are transgressed, would be this square region surrounded by the green dashed line. Once we take interactions into account, however, we can see that this safe operating space shrinks quite substantially to this more triangular dark green filled shape. So we can see that interactions make staying within the operating space, recognizing interactions make staying within the safe operating space more difficult. We can also plot out where we currently are with respect to that safe operating space. We're quite a long way away. And we can also plot out what the effects of some policy interventions might be. Here's on the right-hand side, a range of different BECCS scenarios. That's BECCS stands for bioenergy, carbon capture and storage. You can see that although it might have a very large beneficial effect on climate change, because it has negative impacts on agricultural pressures at the same time, we would at best move parallel to the safe operating space. Whereas a large-scale transition to low meat diets, while the total impact on climate may not be as big as some BECCS scenarios, we're at least moving in the right direction towards the safe operating space. So some implications for policymakers are that interactions are crucial to understanding changes in the planetary boundaries. In fact, our results show that biophysically mediated interactions have more than tripled human impacts on the planetary boundaries. We found that most interactions are unfortunately amplifying. This gives rise to the prospects of cascades of impacts throughout the Earth system, but also scope for substantial synergies, because if you improve the state of one component of the Earth system, that will then have beneficial cascading effects on the others. And this triangular shape of the safe operating space also illustrates some trade-offs that happen between the different boundaries, and maybe the need to choose between high agricultural impact or high climate emissions, carbon emissions. Some of the limitations of this work are that it's at a globally aggregated, so very coarse scale. This is something we're trying to overcome in current work. As I mentioned, we only used Earth system processes. This is directly related to the planetary boundaries. We have feedbacks, but they're only linear feedbacks, not non-linearities. And we also had a fairly limited literature survey, which still left several interaction strengths unconstrained. So to summarize, I've shown you a social ecological survey of interactions between the planetary boundaries. Our results showed that the planetary boundaries are densely interconnected and that interactions have amplified human impacts on the planetary boundaries. We showed, as represented by this last diagram in the bottom right, that interactions shrink the safe operating space for humans in the Earth system, and that interactions also affect our potential navigation towards this safe operating space. And as I said, we have some work in progress where we're doing this interaction and safe operating space analysis at a regional scale, which will hopefully get us closer to a scale where this analysis could be used to inform decision-making by actors such as companies, countries, financial investors, cities, so on and so forth. Thank you very much for your time.
Thank you very much for your talk. If there are any questions?
I believe Steve is on the line on the phone in case everyone wants to ask him direct something.
There's no questions. So
I'm sorry, I have a question.
Okay, please.
Now, this is a wonderfully interesting talk, but I didn't catch at the beginning, how did you quantify the interactions?
Steve here. Quantified the interaction. Sorry,
we cannot hear you well. The connection is not good.
We took the from literature, from papers.
Okay. All right. Thank you.
Okay.
So if you give me your email, I can put you in touch through email so you can continue the conversation there.
Okay. All right. We can do it later. Thank you so much.
Thank you very much. Then we go to the next talk, which will be delivered by Karolina Safarzynska. And the title of the talk is Multiple Inequalities in an Agent-Based Climate Economy Model, Implications for the Social Cost of Carbon. Yes, please.
Sorry for a second. Hi, everyone. I will go live, so I will just put my timer. And welcome. Today, I would like to present an agent-based climate economy model, which we will use to study the distributional consequences of the social cost of carbon. And the motivation for our approach is pretty straightforward. Like we have, since 1950s, we have constantly increasing carbon dioxide emissions, and we are not able to reduce it so far. And even with the COVID-19 situation, where we hoped that this will actually bring at least the reduction in the emissions, we now see that this is not happening. So we have a lot of disagreements in the literature how to tackle this increasing emissions. And some people say we can distinguish 4 of them, with some people putting huge emphasis on technological solutions, such as diffusion of renewable energy. But we have to realize that even if we manage to make electricity sector 100% renewable, we still will use a lot of fossil fuels, because we use at the time like at most 30% of electricity in the total energy use. So this solution will not prevent global warming. Other people say that we need to change consumer behavior, and there was a lot of emphasis on the degrowth of material and consumption. However, as I mentioned just a second ago, with COVID crisis, which actually brought us a huge decrease in consumption, we still haven't observed like a proportional decline in emission. And this is because our system is so dependent on fossil fuels that it is very difficult to stop those forces. So economists say that probably the most viable solution would be to introduce financial incentives such as carbon tax, which will lead to pricing of all the product and processes in a way that they will reflect the environmental emissions. So this way we will have like market forces which will allow us to reduce emissions just by pricing. And there are 2 lines of literature which focus on this, which we will try to bridge in my presentation. And one is the models of Nordhaus, like type of models of Nordhaus, which are integrated assessment models, which are highly aggregated, and they are used to calculate the optimal value of the social cost of carbon. And another line of literature which takes this value and study its distributional consequences. But what is very important to emphasize, so one line of literature will study this co-evolutionary dynamics between the economy and climate, but paying no attention to distributional effects because there are no network interaction, whereas the second one is studying distributional consequences, but like in very static models in one time, usually. Yes. So what we've done, we proposed an agent-based model, which instead of focusing on these aggregate equations, we created an economy which is composed of networks. Here, wherever you see firms, this is a network of firms. We have a network of banks, network of consumers and power plants. And what we did, we calibrated at the global level so it replicates the aggregated model of Nordhaus. And maybe what is important to emphasize that in such models, you usually have many equations, but like the main dynamics are driven by just 3 in those models of integrated assessment models. One will tell you how consumption changes over time, one accumulation of capital. So people, if they don't consume something, this will be saved and invested in capital accumulation. This will lead to output growth. And this will generate the secondary effect of increasing emissions. So you will have the third equation, which will reduce the output. So in this model, we calibrated all the interactions so they generate the same global dynamics, and we calculate the total loss of output as a result of climate change, which is endogenous, of course, to the model. But then instead of reducing total output, we will distribute all the damages among individual consumers. And to do this, we adopt a very nice function from Denning paper. So what these authors did, they took a Nordhaus model and still using the aggregated equations, they created one simple formula which allowed to take the total total amount of damages and distributed between different consumption quantiles, which is still aggregate model. So we will go one step further, and we will disaggregate it among individual consumers who will make individual decisions, how much to consume, what to consume. And we study different types of wealth distribution and different types of tax recycling revenues. And our goal was to conceptualize transmission mechanisms between three types of inequalities in the model, namely consumption, income, and inequalities. That's basically the function. So we will be studying using this one parameter, like how we distribute damages among individual consumers, and we can do it proportionally or inversely proportionally to the income, or just distribute damages uniformly. So those damages will reduce budgets of individual consumer, and the result of which they will buy fewer products. But what is important here to emphasize that in each time step, we'll keep the total damage constant, and it will be equal to the amount predicted by Nordhaus. And what we find is that how we distribute damages, it is crucial for the value of the tax itself and for the climate change. So what we find, here you see the social cost of carbon over time, and this is a rise in the global temperature. The bow, which is a solid lines, reflects simulation runs without the tax. And here, when you have like dashed lines, you see how much the increase in temperature is reduced by introduction of the optimal carbon tax. So if this graph is showing that if we distribute damages uniformly, that everyone suffers the same kind of amount of damage, or like if we distributed inversely proportionally to wealth, which means that the poorest households suffer the most, we will get close to the predictions of Nordhaus. But what is really surprising is that if we distributed it inversely proportionally to wealth, meaning that richer suffer more, this will result in the lowest social cost of carbon and lowest emission. Of course, this is very difficult now. Why would rich suffer the most from climate change? But actually, empirical literature is not conclusive on this topic. We don't have any empirical studies showing how within a country damages will be distributed. And we can imagine that if you have more capital or larger farms, you will also incur a higher share of damages. But this is actually an empirical question which we cannot answer. We're just doing a simulation of this at this stage. And why is this surprising result? I will just illustrate it shortly with the very static analysis. So here you see how the demand of two agents, or if you have economy composed only of two agents, and one is rich and one is poor, and we studied, say, total demand depending on how damages are distributed. Here you see the demand if the poor suffer the most from climate change, and you see that this is higher than the total demand if the rich are the most affected by climate change. This is the size of the damage. And why is that? It's because it's closely related to how many products and by both of those people. So poor people usually buy fewer products, so their demand is less crucial for the stability and the demand of individual firms, which if they go bankrupt, this can generate a whole cascade of bankruptcies in the firm network, and which can spread also to the financial network, causing the collapse of some banks. So the basic idea here is that richer households buy more products and generate more stable demand, which prevent those cascades. But we, of course, show theoretically that this effect depends on the total wealth of the country and how the wealth is distributed within the country. So one of our main findings is that we were studying and quantifying the transmission mechanism between income inequalities, wealth inequalities, and consumption inequalities And our model was allowing us to do this because we have all those disaggregated dynamics. And after this, we were also checking what will be the difference if we spend all the tax carbon revenues on, for instance, tax rebates, which means that it goes back to consumers. And we were comparing if we collect all the tax revenues and then distribute it equally among each consumer, which is the most popular way to distribute carbon tax, or the idea of how people want to do this in the future. Or we also generate some scenarios where we targeted the poorest households the most, so they were getting higher benefits. And we compare it to the situation when we collected all the revenues and devoted it to investment in renewable power plants. And what was surprising, that those investments, such a use of carbon tax revenues, was more equitable than those tax rebates. And why is that? It's because in general, no matter how high tax is, of course there is a certain value, but we are talking about the optimal value of tax. The benefits which go to individual households are too small to generate a huge impact on consumption inequalities and income inequalities, contrary to investment in renewable energy, which actually has a huge boost for employment, and this way is reducing consumption inequalities even more. But this comes at the cost of generating higher wealth inequalities because of the concentration of rents, energy rents among consumers. And I guess it will be this all for now. Thank you.
Thank you very much for your talk. If there is any question, if there are any questions, please speak up, the one that wants to ask a question. We have no questions. Then we'll go, thank you very much again. We'll go to the next talk, which is wait a minute. Okay, it's ready in front of us. Unveiling the infodemic mindset linked to the climate emergency. And the talk will be given by Roger Cremades.
Good afternoon, everyone. My name is Roger, and I'm presenting this joint work with Massimo, Stella. I'm very happy to see many colleagues in the list of attendance. I send to everyone, indeed, my warmest greetings. I would like to talk today about the climate infodemic and about how can we use network science and information science to unveil the different messages that occur in the climate infodemics. So with this purpose, I will introduce the topic, show how we selected data of public interventions by prominent actors, both in the climate activism side and in the climate disinformation side. I will explain the methods based on mental lexicon and mindset networks, and I will provide results for Greta Thunberg and for Christopher Monckton on a number of words in their discourses, keywords in the climate debates. And I make some conclusions to finish. So let me start with the introduction. If you go to YouTube right now and just introduce Madrid climate event, in the first position, you see a talk by Greta Thunberg. But in the 18th position, you see a parallel event organized by an American think tank, which is apparently funded with the objective of spreading false information about climate change. And we think this is very worrying because climate disinformation is an obstacle to climate policy. And we are in a climate emergency. So on the basis of that, we need to understand how to differentiate both messages. And we need to understand how could we provide information to tools flagging such messages. And with this, this is already part of the aims and the research questions. So how can we unveil infodemic content linked to the climate emergency? And can we use semantic patterns to unveil emotionally distorted content linked to polarization? Is there a mindset associated to each side of the climate divide? what are the differences between Fridays for Future and people coming from institutes that are funded with the so-called institutes that are funded with the objective of distorting information about climate change? And is there a way we can limit this negative influence? So the data that we collected is formed by a roughly equivalent number of words coming from 11 public speeches by Greta Thunberg, which I guess most of you know is a well-known climate activist, and 3 much larger speeches in 2019 by Christopher Monckton, who's a climate disinformation protagonist with a very strong track of activity. If you check the Wikipedia page, you will find something unbelievable things coming out from this person. And about the methods, first I will introduce how we use a mental lexicon, which is the cognitive counterpart of the brain circuits. It's an idealized system apt at acquiring, storing, processing, and producing language ultimately. So we cannot introduce the mental lexicon in the lab and do some experiment with it, but we can access the associative structure of knowledge in it via the speeches that we are analyzing. So once we have these speeches, we convert them into words and we see how these words are linked. We then next take and see that when we read language, we don't see the structures of conceptual associations between them, but these associations are there and come from the mental lexicon. And what we do is we build mindset networks or forma mentis networks. Forma mentis in Latin means the shape of the mind, which encapsulate linguistic knowledge coming from the mental lexicon. What do we do with this linguistic knowledge? We interpret neighborhood in sentences as semantic frames and compute the emotional perceptions in relation to an emotions lexicon linked to any of the words. So as you can see here, we see the conceptual associations that come together in this sentence. Failure and success are both sides of the same coin. Learn how to face failure. We see how the emotional perceptions of failure relates to some emotions, other success relate to other emotions. There are neutral words like side, and I will explain this more when I present the results. So here we have these forma mentis networks for the word climate. In the left side, we have the forma mentis network for Greta Thunberg for the word climate. And in the right side, we have the same for Christopher Monckton. And down, in the down part, we have the emotional profile to see how these words in the network relate to the emotional profile. We have that the links, when they are gray, blue, red, they indicate syntactic relationships, and when they are green, they indicate synonyms. And when the words are blue, they indicate positive words. When they are red, they are negative words, and when they are black, they are neutral. So words are bigger if they are more present, and links are colored if linking at least one, a positive, negative, and neutral word. So if we focus on the left side, we see how it illustrates that climate activism perceives climate as overwhelmed by danger and breakdown and a threat that it's necessary to fight. But if we go to the right side, we see that climate disinformation actors associated climate with neutral concepts expressing inconsistent science. And this dichotomy reverberates in the mental construct of change later, which is a neutral word on itself on the common day language. So if we analyze on the left side, same legend interpretation as in the previous figure, if we analyze the left side, change is associated to concepts strongly eliciting anger and fear, as here in the emotional profile we can see, but also to trust. And is an emotion identifying outstanding visionary leaders. And climate activism gave relevance to break down danger and threat before, which are concepts characterizing charismatic value-based mindsets and even revolutionary speeches. Stunningly, in climate disinformation, such threatened perception is completely absent. There's nearly no anger, there's nearly no fear. And it's related. And here we see a lot of trust, and trust is related to a wide variety of trust-evoking associates about attempts to convince the public with alternative facts on global warming. So this trust is only apparent, and it is interesting to see that only climate disinformation actors make negative associates like hysteria and catastrophe. It's the only place where these hysteric responses are present in the climate disinformation side. So I will go through a few more words that are interesting. I give a very interesting picture in my opinion. So if we look at action, so for climate activism, it means hope for a better future, much wanted and needed, propositional towards the elicitation of a revolution-like call to action, you could say even a social tipping point. While for climate disinformation, it's just a sad bureaucratic cause, still something positive, but does not lead to any practical safeguarding initiative. Belief, climate disinformation angrily believe there is a scarce contradictory evidence, while climate activist beliefs are strongly propositional about setting goals to avoid the danger of inaction. Children, interestingly, is an angry concern for climate change disinformation actors. Climate change activism perceive children with trust and joy, but sadness for their anticipated future. Scientists are perceived as isolated prophets that provide facts for narratives of climate disinformation around changes in solar radiation that are a source of anticipation. Instead, for climate activism, they are people that politicians need to listen to, experts that solve problems. Just a few more words. Future, relatively absent in climate disinformation, inspires trust linked to future awareness in climate activism. Leader, someone to trust and follow in climate disinformation, attention here, but who triggers anger linked to politicians and emissions in climate activism and still inspires trust. Life, climate activism uses this term carefully, associating life to trust to conditions of human survival and planetary justice, while climate disinformation doesn't display a current pattern. Number, climate activism stays positive and lacks objections to numbers coming from current science, while climate disinformation displays an opposite pattern of strong anxiety projecting into the future a sense of exaggerated imbalance on the issues at hand. Science, inspiring mostly negative emotions of anger, disgust, and fear to climate disinformation. It's a matter of trust associated to listening and numbers for climate activists. So I will briefly come into conclusion. So the Friday for Future speeches by Greta Thunberg promote climate change as a fierce fight, a call to action, combining anger, trust, and hope, which are cognitive traits of charismatic leaders and revolutionary movements, as we found in the literature. Climate disinformation, instead, associates trust eliciting concepts to change, while vehiculating an implicit perception of climate relying on fear, hysteria, and alertness about inconsistent science. We see that infodemics on these negative emotions can greatly harm social consensus about climate change, in turn hampering policymaking, and this urgently motivates the adoption of novel cognitive tools exposing such detrimental infodemics in a way that they could incorporate findings and signs such the results we are producing into online automated tools that could flag content negatively. Thank you. I'd be most glad to hear some questions.
Thank you very much for your talk. There's a question in the chat, but Galbraith can say the question by himself.
Please.
Sure. Thank you. I was wondering about the emotional lexicon that you use to identify the emotions associated with the words. How did you decide on which lexicon to use?
So I can provide you the source of the lexicon. I can provide you the reference of the lexicon. What I cannot tell you is why we decided with this one, because I did this work together with Massimo, and unless he is in the room right now. No, I'm sorry, Elroy. I'd be most glad to follow up by email.
Okay, thank you.
My pleasure.
Is there any other questions as we have some time? or some question to the other presenters? Okay, I would like to thank all the presenters for keeping the time and also the interesting work, and also the attendees that attended this session. And I would like to conclude the session and wish you all the best for the continuation.
Thank you.